Hi, today we're going to do a video on conventional milling versus trichordal milling, if that's how you pronounce the word. The reason we're doing this is because there's sometimes some older managers or people who used to machine who think that taking the full depth of the end mill or the full width when plunging it is faster than taking a small slice. And we're going to compare those two today with a stainless steel flange. So let's go to new design. That's not new design. Untitled. And we're making a flange. It's going to be a 6" by 1" flange again. 6. Extrude that. -1. Go to top view. And we're making the slots in this. So we'll do a new sketch on the top surface. And put a slot about 45 degrees in the lower right, lower left. And make it 750 diameter. We'll take a line from center out. And this is going to be our 45 degree. We'll tab to the degrees. Type in 45, press enter. Now we'll take a coincident from the top. Highlight the circle. And highlight the line, which they look like they're already coincident, so good. Now we'll take another line and we'll touch the outside of the circle and just drag a line out. It can stay connected because we're going to take another line, the third line, to tangent right there. And what we want to do is make a tangent lines or parallel lines to our 45 degree line here. So we'll take parallel from the top, highlight one of the lines, our 45 degree line. Now that's parallel. Highlight the other one. Now they're both parallel and tangent. But we can see that our 750 diameter is not. So let's go back to coincident. Highlight the dot, the center line of the circle, or center point, and then highlight the 45. Click. Now it's coincident. So we'll rotate that a little bit and we'll extrude that or cut that. And just highlight what we need. That, there, there. And we want it to be -1 as well. So it's a cut all the way through the part. And we don't want to leave sharp corners there, so we'll add a little chamfer to the sides, maybe a 30 thou. Chamfer. 2 edges, 30 thou. Alright. And we'll do the top lines alone and the bottom. Alright, so let's go to pattern, circular pattern, and we want to select faces, zoom in, 1, 2, 3, 4, 5, and we'll select the axis we want, which can be that face or something else that's has a center around the part where you want your slots to be. And there we go. Now we have 4 slots. A little bit big. Let's put a diameter or a dimension on the center line of that slot real quick. From center to center. Let's make it 2 inches. That looks less ridiculous. It looks better. Alright, so that's our isometric view. We are going to mill those. We're going to mill one the old conventional way, FOG style. Let's go to manufacture, setup, new setup. Our stock is going to be fixed size cylinder, 6x1 on center. Our setup is different. Let's tell it that our setup is, our Z0 is not that face that's highlighted, it's this one. Oh, it thinks we're in turning. Let's go to milling and now do it. Stock is fixed size cylinder again. Stock diameter is 6. Length is 1. We can select the axis we want. It's going to be on that center line. Z axis. Now home is going to be there. This is setting up G54, so we want Z G54 0 on the top of this plane, and then X and Y 0 can be there. The rest will stay the same. Post process we're not worried about because we're not going to post it. We're just going to check times. So we'll take that. Now let's take a 1/2 inch end mill because we're standardizing. We don't need to have a 750 slot end mill. Let's go with 1/2 inch end mill contouring, and we'll do this the old way. So we'll highlight our lines, our geometry first, and we'll hold Alt or Option if you're on a Mac to highlight individual lines. And now we have 5 lines and our arrows are all pointing in the right direction. And I already set up this tool because it was in one of my templates. So most of my heights are all set the same. All to the top, model top. The bottom height is set to selected contours. Now I'll change that because I selected the top of the part. Now I want the bottom. So I'll press selection and I'll just highlight anything on the bottom and it'll go 50 thousandths below that. And since we're doing this old school, let's change our feed rate to 40. No. We'll go 100 SFM, and then we'll do 1,500th per tooth, which is kind of slow. Let's go 125 and give it a chance. 954 is kind of fast too. 110. There we go. 840. Let's go make it a 4-inch feed rate, 4 inches a minute, and that looks good. Let's just change everything else to 4, so there's no stray feed rates in there. But we're going to do multiple depths, and the old way people would do is a little bit more than the diameter of the end mill in depth. So let's go. Let's start out with 500 deep with a finishing pass of 500 as well, and tell it we want even step down, so it's not, if we're a little out, we're a 1-inch flange with 50 thousandths extra, so it'll probably do 525 deep at one time. And that's what we're doing there. We're just going in, coming out. Now let's see what we get. We're not ramping in. We are adding a tangent of maybe 300 thousandths. So we don't want to drop down onto the material. We want to start outside the material, drop in, then mill into it instead of plunging into the part. And we'll see what we get here. Press OK. It's 3 minutes, which doesn't sound bad. It's 3 minutes there to do this operation. That's kind of fast. There we go. And that looks normal. Except, how long is it going to last? We don't know. Most guys would cut steel like that. 316, you're not going to cut like that. You might get one part on one end mill. Let's do the same thing with trochoidal milling. We'll take that, what we have there, we'll right click, create derive program, and then do adaptive clearing. Now I already have an end mill in my template that does that already. So I'll go to my template files in the cloud and go to 1/2 inch end mill, adaptive clearing, select. Now this one's mine. It's set up for steel, high end, low end of steel, kind of high end of stainless. It works is what it is. The feed rate's not bad. Now what we're going to do is just go in there one time, one depth. So we have to highlight everything. And we're going to do that from the bottom this time. 1, 2, 3, 4, 5. I don't like that last one. Take that off. 5. Alright, and we would do a lead in of 300. Not a vertical lead in of 300. Make that 20. And see what we get. Now you can see one of the feed rates, one of the times it takes is 3 minutes 20 seconds. The other one is 6 minutes 10 seconds. Double. A little bit more than double. Why is that? Let's see if we can change some things around. And we will go to no engagement feed rate of 300. That took off over a minute. Okay, now let's look at what this does. It's the same feed rate, or same slot, except we're going in, cutting out the area, side milling, full depth. And we didn't check what our side depth of cut was, and that is back here on passes. Our load is 50 thou side. That's just not bad. We can take off the stock to leave, but I think we can go to a higher feed per tooth, because this feed per tooth is based on the end mill's forward cutting radius. So the tip of the tool is taking 1/1000th, but we're no longer using that. We're using the side of it. So you can actually double that at the min. So let's go 3 thousandths per tooth, and our feed rate jumps to 17 inches a minute. And sounds fast, but it is not fast. There's a section in the Machiner's Handbook that explains why this works, why trochoidal milling works. I'll put the page number on here, and you can reference it, and I'll reference the volume. That usually helps out a lot for teaching these FOGs who don't know how to mill the modern way, I guess, which is not a modern idea, but still, they're used to plunge the end mill depth and just feed across, and it sounds terrible. The end mill doesn't last. This type of milling, your tools are more predictable, they last longer, and it's proper milling. You're using the whole end mill flute instead of just the bottom third or quarter, which is a waste. So let's hit OK, see what our time changes to. 2 minutes 19. Now let's do something here so we can see a separation here. We're going to change the geometry to a different slot. That way we can show both of them in the simulation, which is, it's okay, I should have did it the first time. Here, 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 and here, and then press OK. So now we have that toolpath, and we have the conventional toolpath. Let's highlight both of them. There we go. Command on a Mac. Does it do the same thing? Yes. Does it totally different? Yes. Is one better at milling? 100%. The one on the left here, this is like milling like if you were on a manual machine. You probably couldn't even go that fast on a manual Bridgeport. But on a CNC, you could do it, and it would probably last longer with better coolant. It'll still get the job done, but it'll still wear your tools out. The other trochoidal milling toolpath is much more effective in using your tools. You'll get a better milling cut. Your end mill will wear evenly across the top of and the bottom of the flute, and your feed rate's higher. Even though you're taking a higher tooth, your side load is much lower because you're no longer cutting with the tip of the front of the end mill. It's not the brunt of the end mill. You're cutting with the side of the end mill, which is when you have a crescent, you have the full width of the crescent here, but as you go over to the side, that crescent gets real thin, and that is no longer 1/1000th per the recommendation of the handbook. So if you increase your feed rate, that has to increase there, and that's where your 1/1000th will come into play instead of up here at the top of the crescent, or the center of the crescent. That's what makes this different. So let's press simulation, and we'll watch it. Simple path, 3 steps. Now, same tool, and it's taking a bunch of steps. It looks like it's a lot of waste, but definitely not. It's probably the best way of milling. If your machine has enough space to hold the data for the G-code, I would suggest you do it. The other way, you could probably get away with a sub-program on a very old machine that didn't have a lot of space. But modern machines have a lot of space, and you can run this G-code. It's probably several thousand lines, but still. I would suggest you try this out. This by no means is the proper feed rate for your machine, You should do it on your own. Your mileage will vary. I have more experience on what the machines I run, how they react when I machine like this. Your machine may be different. You may be running an old Morisiki. It doesn't have a 10,000 RPM spindle, or you may be running a machine that has a 12,000 RPM spindle, and it can do that. Like if you're running aluminum, those speeds are way high. Almost any machine should be able to handle these low speeds. These are stainless steel speeds. But try it out, see what you think. If you got anything out of this video, like and subscribe. If you have any suggestions for another topic for Fusion, let me know in the comments. That's it.